complete inner product space is called Hilbert space. Okay, so Hilbert spaces are what we deal with in quantum mechanics. State space of any quantum system is regarded as a Hilbert space. So Hilbert space essentially is a complete inner product space. That means it's a vector space on which inner product is defined and then has the property of completeness. So in whatever remaining lecture today, I will try to prepare the ground to define a Hilbert space. Essentially define completeness of a space. For that, essentially we have to define some more properties. Now once we define the structure, inner product structure on the space, we can define one important property called if V comma U, the inner product is equal to 0, then we say V and U are orthogonal. Two elements of vector space are said to be orthogonal if their inner product is 0. But as I told you, the inner product can be defined according to your convenience. Okay. For example, I can define the inner product V comma U as I told you earlier, sum of J Vj star into U. I have defined it this way. But more generally, I can put in some weights here, Wj, such that Wj is greater than or equal to 0 for all j. So an arbitrary weight factor given to each one of this term will also qualifies to be an inner product. In general, you may take Wj to be equal to 1. But even if I put in an arbitrary Wj, I can define an inner product. So the orthogonality cannot be arbitrarily discussed. Only once you define an appropriate inner product, with respect to that inner product only, one can talk about an orthogonality. Because orthogonality of two vectors depends upon what is the definition of this inner product. In essential, it depends on what are the weights. If you choose weights to be 1, it may be orthogonal. If you choose weights to be different, it may not be orthogonal. So it depends on what is the orthogonality. Orthogonality, please remember at this moment that orthogonality is linked to the definition of inner product. So with respect to the defined inner product, you can say that two vectors are orthogonal. Two elements of the vector space are orthogonal. Now,
is that okay when Wj is equal to 0?
Yeah, for some things you can have 0 weight. Doesn't matter.
You said that there are different ways of defining inner product.
Correct.
These different ways can be mapped into this weight factor as well.
Yeah, so that is, you may have another way of defining it also, but if you define it this way, it will satisfy all the. This is one very general construction, but which satisfies Vv is greater than or equal to 0. It induces a norm. But you can have any function from V cross V tilde to complex numbers satisfying those axioms as an inner product.
So all these possibilities can be
we cannot say that this exhausts all the possibilities. You may have some other possibility also.
So it's a linear way.
Correct. So, linearity is required for us because that's a part of the axioms. But by no means I can say that this exhausts all the possibilities, or this is the only possibility. This is the most general possibility that we can think of, very useful in many applications. So I can, but you can always construct. See, no construction business can be exhausted. And there is no general theorem I can prove that every construction can be mapped onto this. There is no way that I can prove any such thing. Now, I will present one argument. This argument is due to R. Shankar. There is a book by R. Shankar in quantum mechanics. In the first chapter, he gives this argument to define an inner product for functional spaces. This is, when I define the inner product, I consider a finite dimensional Hilbert space, n-dimensional Hilbert space. But it can be, n can be anything. But then this is the inner product that we thought is appropriate for finite dimensional Hilbert spaces. Now, if you have function spaces, like for example, yesterday we have considered D is equal to f of x such that f is a function from 0, 1 to r. And we know that this forms an infinite dimensional vector space. All such functions. Okay. Now, if you want to understand, you will have, okay, let me put it slightly more generally, could be a complex valued function. Could be a complex valued function. Then its dual, V tilde, will be f star of x such that f is from 0, 1 to c. Same function, but its complex conjugates to be. So now you take my f of x and f star of x, you must construct an inner product. So, what is a suggestion which